Hello, welcome to the Linear Algebra Tutor. My name is Jason. I'll be your host and your teacher in this linear algebra course sequence. We're going to be covering the traditional topics taught in a linear algebra course at the university level. Now, a lot of students say, well, when am I going to take linear algebra? Why do I care? Usually students take linear algebra in a college level or at a university level, usually in their sophomore, maybe their junior year. So usually when you take linear algebra, you've already been exposed to calculus, you've definitely been exposed to algebra and geometry and trigonometry. And what we're going to be doing in this course is learning about these things called matrices and learning about the properties of matrices, how to use them, linear transformations, vectors. It's kind of an amalgam of different topics that are kind of thrown together and called linear algebra. But the single theme that is kind of constant through all of these topics is the concept of a matrix. So what I want to make sure you understand is that what we're going to be studying in this lesson and all the subsequent lessons are definitely taught at kind of a higher level, like a college sophomore, college junior type of level. Usually the people who are taking this class are going to be engineers, math students, physics students, chemistry students, basically the math, science, engineering type of crowd. But the core concepts of what we're going to study here in the very beginning of linear algebra, you've probably already been exposed to in your previous studies of math. So the idea of what a matrix is, the basic ideas of what you probably use them for, you've probably already been exposed to either in high school or in earlier algebra classes at the college level. And what I'm going to say right now is that because of that, because linear algebra takes that material that you've already been exposed to and expands on it, there's going to be a little bit of overlap with what we're learning here and probably what you've already been exposed to. So the idea of a matrix, the idea of an inverse of a matrix, things like that you've probably heard of before, but we're going to go a little bit deeper in a linear algebra setting to more applications, more theorems, and things of that nature. So we'll be going in a little bit deeper than what you've already been exposed to, and of course expanding on those topics as well. But the one thing I would like to say though is I'm trying to create this linear algebra tutor here as sort of a self-contained course. If you've never seen a matrix before, I'm going to explain all of that here. I'm going to treat you as if you really are not an expert in those topics that you probably have already seen before and been exposed to before. But I would like to say that even though I'm going to try to contain it all here and make it nice and neat and easy to understand for you, I want to make sure you understand that I've already produced what I call a matrix algebra tutor. It's been available for many years now. I highly, highly encourage you to get that tutorial series I have and work through that, because some of the same topics are going to be covered in here that we've already covered before, and in many cases I'll have more examples and a little more practice in that previous tutorial. So I'm kind of expecting that everybody watching this has already at least looked at high school or introductory algebra matrices, and probably you looked at my matrix algebra tutor, been exposed to this stuff. But again, I'm not going to assume that you're experts. I'm going to take you through it step by step from the beginning. So in that regard, let's go ahead and get started. So the idea of linear algebra revolves around this concept of a matrix. And a matrix is basically a rectangular array of numbers. Right? It's a rectangular array of numbers. And you say, why do we care about a rectangular array of numbers? Well, we'll find out the applications later on, but basically it allows us to solve equations, systems of equations. Also allows us to bookkeep vectors and vector notation. And as engineers and scientists know, vectors are used in pretty much every type of problem that you'll have. And so arrays are kind of a general class of bookkeeping method where we can take all of these numbers and bookkeep them in terms of an array. So if we have a matrix, usually we're going to give it a label. So in this case, let's call it matrix A. And so it's a rectangular array of numbers. Now, when you have a real problem, you'll have numbers inside of this matrix, almost always. But in your book, you're going to see things in general terms. So for instance, we may have A11, A12, this is another number, dot, 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 A1 sub n, like this. I'll close off the matrix here. In the next row, we might have A21, A22, dot, 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 A2n. So this is the second row of the matrix. And we can have some more rows here. Eventually we'll get to AM1, AM2, dot, 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 AM, And so this is a great example of how things are expressed in linear algebra versus how they might be expressed in an algebra setting, in a basic algebra setting. Like in high school algebra, you'll be told a matrix is an array of numbers, which is exactly what it is. But in a linear algebra book, they're going to show you a matrix with all of these letters running around. So you kind of need to open your mind and make sure you understand all the notation. That's what I'm going to show you as we go along here. So even though I've got a bunch of letters here, you need to realize that this matrix really is an arrangement of numbers organized into rows and columns. So in this particular case, I might have m rows. So this is the number of rows. That's a row, that's a row, that's a row, that's a row, that's a row. However many rows it is, we're calling it m rows. And we can call it n columns. So again, this is a column, this is a column, this is a column. However many of the dots mean I can have some in between. Eventually I have my last column. All right, so what I'm leading to here, what I'm leading up to is because I have n columns and m rows, we say that A is a m by n matrix. So however many rows, however many columns. So in order to solidify this, if I want to make it more concrete, let's say our matrix A is something a little more familiar. Let's give it some real numbers. Let's say I have 1, 3, 4, 2, 1, 9. So this is a matrix, right? So I have a row up here at the top, and I have a row underneath it. And here I have a column, a column, a column. So it's arranged basically like a table, all right? And so we say that this matrix, because it has 2 rows and 3 columns, we say that it's a 2 by 3 matrix. So the first number you list is the number of rows. So we say m, that's m rows. The second number is however many columns, n columns. So 2 by 3 matrix in this particular case. So now you can visualize if somebody says I have a 5 by 4 matrix for you, you know what that means given the example that we have. In that case it would be 5 rows and 4 columns if it's a 5 by 4 matrix. All right. Now that we have the idea of what a matrix is in our head, we can start to talk about matrix elements. So we can talk about matrix elements. Now, whenever we talk about the entire concept of a matrix, that refers to, in this case, matrix A is what we've called it. And that's everything here. The collection of all of the numbers is what we call the matrix. But each individual number in here, or each individual A in here, is what we call an element of the matrix. And so sometimes, especially when you're reading theorems and proofs and things like that, you're going to want to reference a specific number inside the matrix. And so the way we do that is the following. We say, if it's matrix A like that, we say that an element might be referred to as A sub I j, right? Sub I sub j. So for instance, the I, the first index under A, whatever it is here, that's going to be the row. And this guy, the second thing, and the second index here, which is called j, is called the column. So basically we reference whatever number we want inside of the matrix by giving some subscripts. The first one is for the row and the second one's for a column. So I can uniquely identify whatever I want inside of this matrix simply by giving this nice bookkeeping device. So for instance, if I have element A21, what's that going to be equal to? A21. Well, the first guy is the row, so that's the second row, so it's going to be somewhere along here. And the 1 is the column, so it's the first column. Second row, first column, A21 is going to be the number 2. Likewise, if I have A3 or 13, the first digit is for the row, so that's the first row right here. The second number is for the column, which is over here at the end, the third column, so that's going to be a 4. Right? That's going to be a 4. So the basic idea is that a matrix is a collection of numbers organized in an array, or you might think of it more like a table. And we have to talk about, in order to identify whatever is inside of that matrix, we have to talk about the number of rows and the number of columns. And we use those two numbers to basically cross-reference and pull out any element that we want from our matrix by using the row and the column to find that intersection point there. All right, so in the case of a general matrix, this is a general matrix that we have. In this case, we have rows and columns. Notice this case, we had 2 rows and 3 columns. So it was basically a rectangular looking type of matrix. But if we have the same number of rows as columns, then this matrix is going to look more like a square instead of a rectangle, so it's called a square matrix. So if we have something called a square matrix, all that means is that the number of rows is equal to the number of columns, right? Rows is equal to columns. So let's draw one of these guys and take a look. So a square matrix might have 1, 3, 9, 2, 1, 4, 0, 1, 3. In this case, since I have 3 rows and 3 columns, this is called a 3 by 3 square matrix. The word square is just a descriptive word. It's a 3 by 3 matrix. It happens to look like a square. So if it's not the same number of rows and columns, it's going to look more rectangular. Sometimes you see that described as a rectangular matrix. But if it does have the same number of rows and columns, then we have what we call a square matrix. And of course, we can use the indices for the rows and the columns to pull out any element that we want from this matrix and reference it just like we did previously. All right. So now we've talked about the concept of what a matrix is, and now we need to say that matrices are equal. 2 matrices are equal if, or only if, they are the same size, whoops, size has a Z, and I'll change colors to put the other constraint in there, and Aij is equal to Bij. All right, where these are the elements of matrix A and these are the elements of matrix B. So no matter what value I put in for I and what value I put in for J, those are the rows and the columns. Remember, that's how we identify the elements of a matrix, by specifying a row and a column. If I look at the same row and column for matrix B, then basically the two elements have to be the same. So if that's true for every element in the matrix, then we say that those 2 matrices are equivalent or equal to one another. So let me give you an example to show you that. What if I have matrix A, simple 2 by 2 square matrix, 1, 2, 3, 1. This is matrix A. And let's say I have matrix B, which is 1, 2, 3, 1. Right? And let's say I have matrix C, which is 1, 2, 3, 3. Basically what it's saying is 2 matrices are equal only if they have the same size, and every element in matrix A is equal to every element of whatever you're comparing it to. So in this case, matrix A and B are the same size because they're both 2 by 2 matrices. This element is equal to this one element is equal to this one, this element is equal to this one, and this element is equal to this one. So because every single element is equal to the other matrix, we say that matrix A is equal to matrix B. All right, so this is true. Now let's look at matrix A and matrix C. This element is equal to this one, this element is equal to this one, this element is equal to this one, this element is not equal to this one. So we say that matrix A is not equal to matrix C. And because these 2 are the same matrix, we also know that B is not equal to C. So you see the subtlety there. Every element there is equal except just one of them. It only takes one element to be different in order to say that these 2 matrices are no longer equivalent to one another. So that's the only way you can get away with saying those things are equal, is if they're mirror complete copies of one another. All right? That's the concept of matrix equality. Now we're going to talk about something called matrix transpose, right? Matrix transpose. So what we have is for a matrix A, we define its transpose, and we denote the transpose by AT because we're getting the transpose matrix from the matrix A that we started with, okay, by swapping rows with columns. And this is my loosey-goosey definition. If you read a book, a linear algebra book, it's going to have a longer definition. It's probably going to have some more rigorous, symbology in there to show how it's transposed. I'm trying to get the point across to you by trying to cut through some of that stuff. I'm not saying the book is useless. I'm just saying I'm trying to cut through it and make it a little easier for you to understand. So let me show you what a matrix transpose really is. basically, if we have a matrix A, and let's write a real matrix down. Let's say 1, 3, 2, -2, -1, and 1. So this is a matrix. It's not a square matrix because it's rectangular. It does not have the same number of rows and columns. This one has 3 rows, 2 columns, so it's a 3 by 2 matrix. 3 by 2 matrix. Then we define its transpose. We derive its transpose from the elements of the original matrix. Basically what we do is we swap rows with columns. So here's a row, here's a row, here's a row. So if this row is here, we make that into a column, 1, 3. This is a row, we turn it into a column, 2, -2. This guy's a row, we turn it into a column, -1 and 1. So notice how we do it. We do it in a very methodical fashion. We take the top row, make it into a column. The next row, make it into a column. The final row, make it into a column. This is called the transpose of A. That's why we put a little T there. So you can kind of think of it as kind of a mapping. It's an element mapping from one matrix to another according to the rule that you take the rows and you swap them with the columns. That's what we get when we take and find a matrix transpose. All right. And you can also see that in this particular case, the original matrix and the transpose matrix have different dimensions, right? So when you find a transpose, you're very frequently going to get that situation. This is a 3 by 2 because it's 3 rows, 2 columns, so it's a 3 by 2 matrix. This is a 2 by 3 matrix, 2 rows, 3 columns. So you see the same numbers of rows and columns are there, but they're flipped around because of the way we've defined the transpose to be. So let's go and take a look at another example of that. Let's look at matrix B, which in this case is 0, 1, 2, 9, 3, 4, 1, 2, 1. Now in this case, this is a square matrix. It's 3 by 3, 3 rows, 3 columns, so it's a square matrix. So we can then derive from this the matrix that we call B transpose. All we're doing is swapping rows for columns, right? So let's take the first row, 0, 1, 2, and make it into a column, 0, 1, 2. The next row, 9, 3, 4, we'll make it into a column. And the final row, 1, 2, 1, we'll make it into a column. So I have 0, 9, 1, 1, 3, 2, 2, 1, 4. Notice in this case, the original matrix and the transpose matrix has, they're both square matrices, they're both 3 by 3. So if you have a square matrix and you take its transpose, you're going to get another square matrix of the same dimension. But if you have a rectangular matrix like this and you do its transpose, in general you'll get a new matrix for its transpose that has a different dimensionality to it. Because of the way we're doing it, we're taking the rows and switching with the columns, so I think you understand how that works, 3 by 2 and 2 by 3 as we talked about earlier. So we're just scratching the surface here. Again, I'm assuming that you have basically seen some information about matrices. I think you've all been exposed to it. It may have been a while, but you've been exposed to it. But having said that, what I'm trying to do in this course is I'm trying to lead you by the hand, pretend you really don't know too much about it or that it's been a long time, and guide you through what a matrix is, how do we use it, what's it useful for, give you practice problems along the way so you get some confidence. But having said that, even though I'm going to be doing that in this class and trying to guide you by the hand, strongly recommend that you get my matrix algebra tutor, watch those lessons, because you'll get even more experience and practice with a lot of the same concepts that we're going in this linear algebra course. We'll be taking that material that we've already covered in the past, that you've already been exposed to in the past. We'll be diving deeper and exploring the full richness of it. And of course, we'll be expanding on it throughout the entire linear algebra sequence, and you'll understand why linear algebra is such an important class. And you know, I can sum it up in one sentence. I mean, there's a lot of reasons why linear algebra is important. But if I had to sum it up and just say one sentence, I would say that it's so useful to understand linear algebra because it helps us use computers to solve our problems. A lot of times you can take a set of equations that you're trying to solve in engineering and using matrix methods because it's nice and rectangular with rows and columns. See, computers are really great at dealing with rows and columns and indices like that because we can use loops and we can use subroutines to go and plow through a matrix and calculate what we need in a real logical way. We can use engineering, translate it into linear algebra formulation, and we can use computers to solve a lot of really practical problems. That is why I think linear algebra is so incredibly important. Even if you're not using a computer, it's important for lots of other reasons we'll get into, but certainly computers play a huge role into why linear algebra is so important for any student to understand today. So I hope you've enjoyed this lesson. Follow me on this journey into the next lesson and beyond. We'll be studying linear algebra step by step, and I want you to make sure you understand these topics and then follow me on to the next lesson where we will continue.